Okay, welcome to lesson 4.4. In this lesson, we're learning about concavity and points of inflection, and thankfully it's not as long as lesson 4.3. We're going to start with a little bit of a warm-up. For each of these functions, we're going to calculate the first and second derivative, do a really quick sketch of the original function, and then try to think about, well, what does the second derivative actually tell me about the graph? Because that's what we're working with today. So with my first function here, the first derivative is 2x, and the second derivative is just 2. Now when I draw a sketch of this graph, I'm remembering that I can factor this difference of squares, and so it tells me that I'm going to have an x-intercept at -2 and +2. And I know that this is a parabola with a positive leading coefficient, so this parabola opens up. I also know from the equation that -4 is my y-intercept. So lots of information here. What I want to know is, what does this second derivative tell me about what the graph was going to look like? We know that the first derivative tells me that the slope is always going to be 2 times the x value. So if I go over to -2, the slope here must be -4. Or if I went over to like x equals 3, then the slope must be +6 over here. So we're going to keep that in mind. Let's see if we can draw some connections when we have a few more examples. So again, for my second equation, I'm going to take the first derivative and then take the second derivative. And again, I'm trying to find out, well, what does this -6 tell me about this graph? So let's see if we can figure out what this graph looks like. I see here that I have a common factor of -3x. And so this tells me that I have an x-intercept at 0 and an x-intercept at 2. And this parabola has a negative lead coefficient, so I know that this parabola opens down. And this guy here is at 2. And I'm not too worried about this maximum point. I know I could figure out where it is and the height of it. Using the first derivative, I could figure out that x equals 1 is going to be where the maximum is, and then I could plug it in and find the height. But really what I want to know is, what does this -6 tell me about this graph? And then we're going to take a look at a third example here, and hopefully it'll help us draw a conclusion. The first derivative of this equation, now we're dealing with a cubic. And then the second derivative. And we're dealing with some basic functions here, right? No rational functions right now because we're just trying to find a pattern. Again, I can try to figure out what this graph looks like. I see that there's a common factor of x. And then I can factor this quadratic here at the end. Two numbers that multiply to 25 and add to -10 are -5 and -5. So it's the same factor twice. And so that tells me that I have an x-intercept at 0, and I have another x-intercept when x is 5. And you might remember from advanced functions that when I have a factor that's squared, when I come into that x-intercept, I'm going to bounce off of it like a little mini parabola when I zoom in on that. It'll be like the vertex of a little mini parabola. This cubic has a positive leading coefficient, so I know that I'm going to go up on the right, and it's going to be the opposite on the left here. And what's happening, again, remember, is I'm bouncing at 5. If I wanted to figure out where the maximum minimums were, I would set this parabola here equal to 0 and solve, and I would come up with these two max mins. I'm not as concerned about that. What I'm interested in is, what does this line tell me about the graph? And the second derivative is going to help me with the idea of opening up and opening down. So I'm going to solve, when does the second derivative equal 0? So I'll bring the 20 over and then divide out the 6. And on my graph, that's going to be about 3.3. So I'm going to go to my graph and think about this 3.3 here and looking at the point above it on my graph. So what I notice is that before 3.3, the graph is opening down. and then after 3.3, the graph is opening up. And so it's going to help me, this second derivative is telling me where the graph opens up and where it opens down. Notice that in this first example, the second derivative is always equal to positive 2, and the graph always opens up. In this second example, the second derivative is always negative, and the graph always opens down. Here, the second derivative, 6x minus 20, if I pick a number smaller than 3.3, like say 0, and I put it in here, I'm going to get 0 minus 20. I'm going to get a negative answer, and that's why the graph opens down before 3.3. If I pick a number bigger than 3.3, like say 4, if I put 4 in here, I'm going to get 24 minus 4, which is positive, and that's why the graph here opens up after 3.3. So it's going to tell me, and we're going to call this concavity. Concavity is whether it opens up or opens down. And this point here where it's switched from up to down, that's called a point of inflection. All right, so let's summarize. So our test for concavity is I'm going to find the second derivative, and if I find that the second derivative is positive, if it's greater than 0, then f at x is what we call concave up. And so I'm going to see this kind of shape. If I have a negative slope, so this is like my second derivative is negative in this first case, or sorry, my first derivative is negative, but my second derivative is positive, then I'm concave up, but it's kind of decreasing as I go along. In this one over here, the first derivative is positive, so I see positive slopes, but the second derivative is also positive, so it scoops up. So we kind of got these different cases. So second derivative is positive in both of these cases. In this one over here, we're talking about concave down. Now over here, I have positive slopes. I'm increasing. So my first derivative here is positive, but my second derivative is negative. And what that means is I have a very positive slope, but it's decreasing. So I had a large positive, and now it's a smaller and smaller positive. So I'm decreasing because my second derivative is 0. Over here, I'm starting with a negative slope. So my first derivative is negative, but I'm concave down, so my second derivative must also be negative. And that means that my slopes must be decreasing, right? If my second derivative is negative, my slopes are decreasing. And that makes sense here. Here I'm starting with a relatively flat negative slope. So this is a small negative, and it's getting to be a bigger and bigger negative. So the slopes are decreasing in value. Here, when I had a positive second derivative, that tells me that my slopes are increasing. And you can see that same idea in these two pictures. Here, the negative slopes are getting smaller negatives, which is an increase, and here the positive slopes are getting bigger. So when I have the second derivative and it changes sign at some value a, then I call the point A with its y value a point of inflection. And here we can see it. I'm switching from concave down to concave up, or it could be vice versa. Maybe I switch from concave up to going to concave down. Usually I find these points by figuring out where the second derivative is equal to 0. And I'm going to say a little bit more about that later. Okay, so our first example, we're given the graph of y equals f at x. So here's some sketch of a graph, throw some arrows on the end of it. I want to figure out where is the first derivative positive, 0, and negative. So hopefully you're pretty comfortable with this. I'm just going to set up these 3 different statements. So first we'll look at where is the first derivative negative, where is this first derivative positive, and where is the first derivative equal to 0. Sorry, I started really far down there. Okay. Okay, so the first derivative is negative when the graph is heading down. So I can see that. I'm going to erase some of this highlighting afterwards. I can see it here, and I can see it here. I also have a negative slope. And so we'll assume that that point here is at x equals 4 in between the two values. So I've got the two intervals of decrease or negative slope, and then then we'll look for where is the graph increasing, and we see that here it's heading up and here it's heading up. And again, I'm listing the x values here. I don't care how high it goes. I'm interested in the x values. And then finally, where is the first derivative equal to 0? So that's going to be where are the flat points on the graph. So I see that at 3 different points. I see a flat point when x is -4, 0, and +4, right here, here, and here. All right, part B, it says where is the second derivative, positive, negative, and 0? So remember, this is where I'm looking for the scooping up or scooping down, the concave up or concave down. Okay, so first looking for where is the second derivative negative. So where does it scoop down? So I'm looking for, this is a down, oops, sorry, this is a down, and this guy here is an up scoop, right? So looking for those concavities. And I can see that it's starting like so here it's concave up, right? Here I'm concave up, and then at this point here it seems to switch, and now I'm concave down. So concave down, and again it looks like it switches somewhere in here, maybe here at this point here. So I'm concave down, and then we're concave up over here, and concave up over here. So I'm going to say that I'm concave down from -2 to 3, and concave up on the green sections of the graph. All right, so where does the second derivative equal 0? It's going to be, because this one is a polynomial graph, I know for sure it's going to be where the x values, where the concavity switches. Those are going to be points of inflection where the second derivative is equal to 0. All right, part C says state the critical numbers. Remember, critical numbers come from the first derivative is equal to 0 or the first derivative does not exist. So we can't forget that. We're going back to the first derivatives when we talk about critical numbers. So I'm looking for the flat points, remember? So flat points or like vertical tangents, that kind of thing. So I see a flat point at -4, at 0, and at +4. And that makes sense because we can see some maximums and minimums there. All right, points of inflection. We saw the points of inflection here at -2 and +3. That's where the concavity was switching. I'm just going to state the x values of the points of inflection because I don't have enough information, even though it does ask me for the points. I can figure out where the height of the x equals 3 point, but not the -2. I don't have enough information. All right, and then part E, it asks me to state the maximums and the minimums, and then what is true about the first and the second derivative. And this is another learning point for us. So there is a minimum, there's two minimums and these are coming from my critical numbers. And there's a maximum at x equals 0. So now I want to think about, well, what do I know about the derivatives? at those points. So we've already stated that I know that the first derivative is equal to 0 at all three of those numbers. Now what I want to consider is what is true about the second derivative at these values and what is true about the second derivative at these values. So I'm asking about the concavity at these numbers. So -4, I've got a lot going on here, hold on. At -4 and +4, those are both minimums. I want to think about what is the concavity here. Well, the concavity is scooping up and scooping up. So that tells me that the second derivative is 0, or sorry, is greater than 0 at those points. Another way, or you can think of that as the second derivative is positive there. Now when I look at a maximum point, like this point here, and I consider the concavity here, it's scooping down here, or concave down, and so I have a negative second derivative. And this is the basis of the second derivative test. So sometimes on your test, I'm going to ask you specifically to use either the first derivative test or the second derivative test to come up with the conclusion of whether you have a minimum or a maximum. So it's the part of the sentence is going to change. When we're using the second derivative test, we're going to first look for our critical numbers, and then we're also going to consider the value of the second derivative. So first I come up with the values of a by setting the first derivative equal to 0 or finding where it doesn't exist. And then I consider the value of the second derivative. If the second derivative is greater than 0 or positive, then I have that concave up shape, so I must have a minimum. And then vice versa, if I find a critical point, so there I use the first derivative to find it, and then I check the value of the second derivative and it's a negative number at that x value, that means that I must have a concave down shape, and so I must have a maximum at that point. All right, points of inflection. The point C, comma, the y value at C, is a point of inflection if the second derivative changes sign. So I have a point of inflection if the second derivative changes sign at a certain value. So that's going to be that the curve goes from concave down to concave up or vice versa. So to find a point of inflection, what I'm going to do is it's similar to finding critical numbers. I'm going to set the second derivative. So instead of the first derivative, it's the second derivative, find out where it equals 0 and find out where it doesn't exist. Then I also have to check and make sure that it changes sign at this point. So we're going to use another sign chart. This is very similar to our critical numbers and finding the max min points using the first derivative test. All right, so let's do an example. We're going to find any points of inflection, and then we're going to use the second derivative test to find the local minimums and maximum values. Now, I'm doing two different things here. So sometimes the work I'm doing is related to finding the points of inflection, and sometimes it's related to using the second derivative test to find the local maximum and minimum. So there's two different things that they're asking me to do, and I'll try and label like which work I would do for each question. All right, for both of these, I am using the second derivative, so I do have to start off by finding that second derivative. To find the second derivative, I need the first derivative. So I have a product rule here. I've got a u times a v, so I'm thinking about u prime v plus uv prime, something with x's times something with x's. When I take the derivative of u, it's a chain rule. I've got a 3 on the outside, so I bring it down, leave the inner function alone, subtract 1 from the exponent, and then multiply by the function inside the bracket. The derivative of x plus 4 is just 1. That's u prime. Now I'm going to multiply that by the v. And now I add. This time I'm going to leave the u function alone, and then take the derivative of v. The coefficient in front of the x here is -1, so the derivative of this one is -1. Watch for that. And now I'm going to try to factor this a little bit, or simplify it a little bit before I get going. I see here that I've got a common factor of x plus 4. I'm going to bring it out front. And I can take 2 of those brackets. And then my leftovers here, it's going to be 3 times 3 minus x. And then over here, I'm going to be left with the negative 1. I'll just bring that to the front, times there's going to be 1 of those brackets left. So here I'm going to get 9 minus 3x. Okay, so you might have been thinking, well, if we want the second derivative, why don't we just expand it all out? You can do that. I don't find it that hard to find the second derivative using a product rule, so I'm going to use a product rule here again. I'm going to take the derivative of the first thing. It's a chain rule. Multiply by the second, and then add. Now I've got the first thing, I'm leaving it alone and taking the derivative of the second thing. All right. The other thing I'm thinking here is I do want the first derivative factored at some point, because I know that in order to do the second derivative test, I'm going to need my critical numbers. So I know at some point I'm going to have to use the first derivative factored. All right, now again, I'm going to try to tidy up the second derivative here. I see a common factor of x plus 4, as well as a common factor of 2. So bringing that out front. And then writing the leftovers in the bracket. You're going to see here that I'm going to end up with a negative x term. So eventually I might want to actually pull that negative out front and have it join at the beginning. Here I've got negative 4x minus 2x, that's negative 6x, and I've got 5, and it's negative 2 times 4, so 5 minus 8. And so I actually end up with a common factor in this last bracket of negative 3. I'm going to pull that negative 3 out and multiply it with the 2 in the front, and then divide the negative 3 out of this bracket. All right, so there's my second derivative. So from now on, when I use the first derivative, I'm going to use this line here. And when I use the second derivative, I'm going to use this line here. Okay, so a couple of things that they are asking me for. To find the points of inflection, we're going to create a chart. And to create that chart, I'm going to be using the points where the second derivative equals 0. Oops. And where does the second derivative not exist? Now when I look at the second derivative, it's a quadratic function, it's a parabola, so it always exists. I'm going to look for where does this thing equal 0. Since I've already factored it, I can just set each factor equal to 0. So I get as x is equal to negative 4, or x is equal to negative 1/2 for the second bracket here. So I've got my x values. I've got these 2. I'm going to create a chart. And for this sign chart, instead of looking at the sign of f prime at x, I'm going to look at the sign of double prime. My intervals across the top, now I'm using these values here that made the second derivative equal to 0, sorry. All right, so I want to know what this tells me about the original function, the y. So this chart doesn't involve the first derivative at all. So I'm going to pick some number less than -4. Maybe you pick -10, and we're going to think about plugging it into this second derivative here. Now I've got a -6 out front, and then when I plug -10 into the first bracket, I get a negative, and when I plug -10 into the last bracket, I get a negative, and altogether a negative times a negative times a negative, this is a negative answer. Now, what does that tell me about the original function? If the second derivative is negative, that tells me that the original function is concave down. Or if you're more of a visual person, maybe you draw something like this. I know it's got that shape. I don't need a test point. I know that for x equals -4, the second derivative is equal to 0. That's where we came up with it. And I'm not sure if it's a point of inflection yet, so I'm going to leave that. I'm suspicious about that, but I would need it to change sign on the other side. So I got to figure out if this is positive or negative. So picking a number between -4 and -0.5, I'm going to pick -1, but you could pick -2 or -3. Again, plugging it in here is a -6 out front. And then in the first bracket, I'll get a positive. In the second bracket, I'm going to get -2 plus 1, which is a negative. And this comes out as a positive. And so this actually tells me a couple of things. It tells me that I do have a point of inflection because I switched sign. And I know now that I'm concave up since the second derivative is positive. And so I'm going to have that upwards U shape. -1/2 also came from where the second derivative equals 0. I'm suspicious that maybe there's a point of inflection here, but I need to make sure that it's negative, that the sign switches across that point. So picking some number bigger than -1/2, I'm going to pick 0. Plugging it in here, I'm going to get -6 times +4 times +1, and altogether that comes out as a negative answer. And so I'm concave down in this section since the second derivative is negative. And that tells me that I do have a point of inflection because I switched from positive to negative here. And again, if you're more of a visual. So I know that my graph kind of goes like this. It's going to go down, and then it's going to kind of connect to this piece scooping up and then scooping down again. So we've got our points of inflection. I can write that part. So remember that this was a two-part question. So for part 1, I do know my points of inflection. I know because they switch sign. So this is my answer for part 1. And I'm trying to see, sorry, I don't have the y values calculated in my note here, but you would go and find the y values for this because they asked you for the points. So I would go off to the side somewhere and figure out, and I'm going back to the original function here. It's not called f though. So to find the points, I would say at x equals -4, y is equal to, and oh, this one's nice. I get -4 plus 4 cubed. So this is going to be 0. And this one's not quite as nice for me to do in my head really quickly. So I'm going to leave that as an exercise for you to find that value. I'm going to call it K. You're going to go find that number and you will fill it in here in your therefore statement. All right, because I do want to talk about this box still. And there are some more examples in your textbook, but we still haven't finished the second part of the question, the second derivative test to find the maximums and the minimums. Now, the second derivative test says first I have to find the critical numbers. So to find the critical numbers, I have to set the first derivative equal to 0. So remember up above we had the first derivative, so I want to know when does that equal 0. Remember this was my first derivative. Or I want to know when does it not exist. Now y prime is a cubic function, which is polynomial, so it always exists. All right, so I can see here that the first derivative is going to equal 0 at -4 or at positive 5/4. So I've got my critical numbers. Now, the second derivative test just asks me to plug these numbers into the second derivative. So at this point, I'm doing the second derivative test. So I'm grabbing the equation for my second derivative. That was the -6 times. And here I'm going to get 0 for this middle bracket, so overall that's going to equal 0. And we'll talk about what does that tell me. At x equals 5/4, no wait, hold on. I copied this down wrong over here. This should be 2 times -4. Sorry, not being able to see it all on one screen makes it tricky. But it still comes out as 0. Okay, so overall, this one comes out as a negative number. So you're going to type that into your calculator. You're going to see that it's negative, and I actually don't care what the value is. I can just say that this is negative here. So now we're going to talk about, well, what did these pieces of information tell me? So hopefully you remember that when I have a negative, it tells me that the graph is opening down at 5/4. So that tells me that I must have a maximum. So the critical number, I know that I have a flat tangent here, right? This is what the first derivative told me, and I'm opening down, so it must be a maximum point. So what's going on here at x equals -4? We figured out that there's a flat tangent, but remember above we also figured out that -4 was a point of inflection. And so what that means is I was switching from concave down to concave up at that point, but I also have a flat point. And I'm trying to just go back for a minute and see. Oh, sorry, I drew that wrong. I was going from concave down. This is going to make more sense. So I'm going from concave down. I've got my flat point, and then I switch to concave up. There we go. This is what's happening at -4. So it is both a flat tangent line as well as a point of inflection here. That's what we see. So this one here would just turned out to be a point of inflection. All right, scrolling back up, I want to talk about this box up here. These are cases where I'm going to find that the second derivative equals 0, but there's not a point of inflection. So for instance, remember that the quartic function has like that, it kind of looks like a parabola, but it's like the vertex has been stretched out horizontally. At that point there, I'm going to get a second derivative value of 0, but I'm not switching concavity from left to right of that point. And then the linear function, if I take the second derivative of a linear function, you're going to get x equals 0, and that's because the slope is not changing along that line. And so there's no point of inflection there. It just has no concavity. It doesn't open up or down. And then there's times when we have a point of inflection, but the second derivative does not equal 0. So here, the second derivative does not exist at this point, but it is actually still a point of inflection.